Thank you, Meta. Good afternoon, everybody. And so my name is Jeremy Whitlock. I come from the backwoods of eastern Ontario. Grew up in Petawawa, Ontario, and I work at Chalk River Laboratories, which is the major lab of a company called Canadian Nuclear Laboratories, which is the logo in the bottom right hand of the screen over there. This company used to be known as Atomic Energy of Canada, and it is the Crown Corporation that invented the CANDU reactor, which is the Canadian power reactor, which provides about a half of the electricity in Ontario at this moment. And it is for 70 years, it's been the federal nuclear laboratory where nuclear science has been advanced in Canada. And now nuclear science is also found in several universities and a smattering of other smaller labs, but this still remains the major nuclear laboratory. So it's about 2 hours west of Ottawa. I got a map, a little picture of it on the next picture, or the next slide. My opening slide here is a picture of, this is not Chalk River, this is Lake Ontario, and this is the Pickering Nuclear Station. And so you can see on the right, there's one reactor building, and which is the domed concrete structure. The other building next to it is part of the safety system, but it's not a reactor building. And you also see a wind turbine, which was the first wind turbine in Ontario, and this was Ontario Power Generation experimenting with the technology a number of years ago. Oops. So this is a nice picture of Chalk River Laboratories. It is a little over 70 years old. It was built during World War II, sort of as a satellite operation of, if you will, of the Manhattan Project in the United States. Now, it wasn't administratively part of the American effort, and there was a lot of lack of exchange of information, shall we say, between the two programs. But with the advancement of the program in the States, eventually there was a bit of work that was given to the Canadians who are working here at Chalk River Laboratories to build a heavy water reactor. And that's where the nuclear program in this country got its start. So it was like a lot of good science around the world. It got its start as a sort of a offshoot of a military exercise. It's a wartime expedient. The war ended, and we were left with the world's second largest nuclear program, and we proceeded from there. So we're looking at the Ottawa River on the right there. Ottawa is, we're looking west to northwest, so Ottawa is at the bottom of the screen, about 2 hours, and North Bay is about an hour and a half off the top of the screen. So for this talk, I'm going to spend some time talking about the history of the Canadian nuclear program. I've touched on it just now, and I will continue. I'm going to get into how reactors work, but not a whole bunch of that, but I do want to just make sure we're on the same page on how reactors work, because they're very different from nuclear weapons. There's some aspects of them that are similar. It's obviously all nuclear technology, and there are aspects that are very different. I want to talk about the safety and sustainability, and finally a little bit about contributions to world peace from nuclear energy. So first of all, a little bit about the history. So nuclear fission was discovered itself at the outset of World War II in 1939. These two things happened in roughly the same area of the world, and this was very unfortunate because this was the largest concentration of energy that humans could ever release in one place at one time, and the first application that this was put to was to make a very big weapon at the end of World War II. The science itself, because it was just discovered at the start of World War II, advanced in secret during the war, and institutions like Chalk River Laboratories were created. And this wasn't revealed to the rest of the planet until the two weapons were detonated in Japan at the end of the war. And ever since then, there's been an association in the public mind between weapons and nuclear energy. This is how the science was introduced to the public. So much so that when nuclear energy started to produce things that were for medicine, such as cobalt-60 cancer therapy, which is only possible because of nuclear reactors existing, the confusion was evident when the media covered this event by calling this device a cobalt bomb. The cobalt cancer therapy machine is a cobalt bomb, somehow curing cancer. So the event was overshadowed by the outset of the war, and the science itself went underground. It didn't stop altogether, but you didn't see the science of nuclear fission after a short period being published any longer in the public journals. One place where nuclear fission science was progressing at a great rate was in France, in Paris, and this is the lab of Frédéric Joliot-Curie, the son-in-law of Marie Curie, and he's working with Hans von Halban and Lou Kowarski. So von Halban is an Austrian, Kowarski is a Russian, and they're working in Paris. Both von Halban and Kowalski end up in Chalk River, end up in Canada. Kowarski himself ends up building the first reactor outside the United States in Chalk River. So they're working on the science of heavy water reactors. They know how to split the uranium atom. In order to do that, you need other materials to make it happen. And one of these is to have water in some form. And the best, or there are other materials as well, but the best form of this other material to use is something called heavy water, which they didn't invent. It's a naturally occurring form of water, and it occurs in a very small abundance as part of natural water, and they happen to have in Paris at this time virtually the world's entire supply of this material, which until this point had no real use. It had some scientific interest, but other than that, no real use. So all of a sudden, with the discovery of fission, it was identified as one of the key materials that would make a reactor work, if they were able to get a reactor to work. And by getting it to work, I mean getting the nuclear fission process to be self-sustaining, kicking over and producing energy on a sustained basis. The problem with being in France during World War II is that the Germans are coming over the border. So this science was spirited away to Cambridge, England. And it was one of those dark of the night missions to get the scientists in a ship across the English Channel with the world's supply of heavy water and carry on their research in London. Shortly after that, it ended up in Canada, and that's how we got our start in nuclear science. It was the French nuclear program being moved to London, to England, and then to the colony of England to get it away from the possibility of being taken over by the Germans, I guess. Meanwhile, in Canada, the science of fission is still underground, but we have a fellow who's read enough of it to proceed with his own experiments by the name of George Lawrence. He's working for the National Research Council. And if some of you may recognize the labs of the National Research Council in the bottom right over there at 100 Sussex Drive. In this location, he builds one of the world's first large-scale graphite reactors, which that's a depiction of there. So this is just down the road from Parliament Hill. So the first large-scale reactor in Canada was not at Chalk River. It was in downtown Ottawa. Now the distinction about this thing is that it didn't actually reach a point of self-sustainment. So the fission process did not kick over, and you didn't reach a point of criticality. The reactor didn't turn on. The reason was that his materials were not pure enough. He didn't have pure enough uranium, or pure enough, in his case, he was using large amounts of graphite. And he was really just doing a scientific experiment at the time. So he's doing his experiment on the side as well. His day job is doing radiography for the war effort, and he has permission from his management to build this reactor down the hall at 100 Sussex Drive. And doesn't actually become that famous because he never got his reactor to actually turn on, like Enrico Fermi did in a couple of years. But what he did do was establish Canada at the forefront of nuclear science. And so when it came time to accept this research program from England, these French scientists, and now joined by English scientists with their heavy water, he was the Canadian that led the charge and was given the task of rounding up other Canadian scientists. And they were set up in Montreal, the University of Montreal, and called the Montreal Group. And "Okay, let's go" is actually the quote by Clarence Decatur Howe, the guy on the left, Minister of Everything, during the war, Minister of Munitions and Supply, and he's a fellow that could sign off with his name the equivalent of billions of dollars in investment. He didn't know the first thing about nuclear science. He didn't know how uranium could be used for medicine or energy, but he knew that he had some brilliant scientists like George Lawrence who were telling him that this was something that was going to be big, and they could get on the ground floor by committing to it at this point. So they needed a spot to build a nuclear reactor, and this was at the time, the big structure you see on the right is the world's largest research reactor under construction. This is in 1944. During the winter, that's the Ottawa River again. It looks something like that today. That's Quebec on the other side. Also looks just like that today. Nobody lives across there. There's a few more buildings on this side of the river, though. And the war ended, and shortly after that, in September 1945, we built the first reactor outside the United States. And there's, on the bottom right, is Mr. Lou Kowarski, who was one of the 3 people in that room in Paris in the previous photograph. So this was a small test reactor. It wasn't a production reactor. It wasn't designed, by production I mean to make plutonium. It wasn't a military reactor. It had limited use even as research, but it was the first time that somebody outside the United States had put uranium and heavy water in just the right proportion to get the uranium producing energy in a small amount, and then you can do experiments to see how you can build the bigger reactor at the time, which is the one just over here under construction. So this is the ZEEP reactor here, and that's the bigger reactor called the NRX. So the war ends, and Canada finds itself with the second largest nuclear infrastructure on the planet. The Germans, who we had feared were progressing and making a nuclear weapon, had not gone down that road very far. The British had sent their program to Canada. The United States obviously had a major nuclear program, and we were second. We had atomic bomb knowledge because nuclear scientists at the time, nuclear science, there was not much of a division between nuclear energy itself and nuclear weapons. It was just nuclear science. And so making a weapon was something that we could have gone forward and done at that point. We could have been maybe the second country to build a nuclear weapon at that point. We had the world's experts on heavy water reactors and heavy water chemistry and everything else you do with heavy water. We were realizing that we had the world's mother lode of uranium on our soil, so that was a big advantage. And we had the world's most powerful research reactor under construction at Chalk River. So it was never, that small research reactor was finished, but the bigger one next to it wasn't completed until a couple of years after the war. So we never did contribute to the Manhattan Project or the building of an atomic weapon. The reactor itself was a large research tool with all sorts of flexibility built into it. And the question we had at that point was, where do we go from here? We had said, okay, let's go, but we didn't know where we were going at that point. The answer was to be the first country to non-proliferate, be the first country to decide to not build nuclear weapons. And the choice was made to pursue peaceful applications of nuclear energy using the NRX reactor, which is the one here on the left, finished in 1947. It's a very large structure. This is standing about 30 feet high, and it's very flexible. All these things around the outside of the reactor are ways that scientists can use the subatomic particles that come flying off the reaction itself to discover new things about new materials, to make medicines, to cure cancer. We built our own bigger version on the right there, the NRU reactor, which still runs today, starting in 1957 and still running today. And that's where a big fraction of the world's medical isotopes come from, the reactor on the right. So these 2 machines at Chalk River, way up in the bush of Eastern Ontario, made Canada a mecca for nuclear research, which is unusual, that we were a country at that point known for our prowess during warfare, known for being very good on the battlefield, but also mostly good for our natural resources, lots of water, trees, and lots of minerals. At the end of the war, we were experts on synthetic rubber, on building airplanes, a few other things, and one of them was nuclear science, which was entirely unusual. So the world not only found out that there was such thing as nuclear science at the end of the war, they also found out that Canada was number 2 in the infrastructure, which was a big surprise to Canadians as well. That's when Chalk River appeared on the map. That's when the town of Deep River appeared on the map where I live today, which was the town site built for the scientists. And still very much today is sort of a company town for the laboratory. Okay, so the atomic bomb that saves lives, or the cobalt bomb, this is the first major output from this pursuit of peaceful applications of nuclear energy. This was in 1951, so this is very shortly after the NRX reactor started up in 1947. One of the first things that the NRX reactor produced was medical isotopes so that scientists working at hospitals could figure out ways to fight disease with the energy from not the splitting of the atom, but the thing that results from the splitting of the atom, the radioactive pieces that come off of that in small amounts. So there were two groups working simultaneously, one at the University of Western Ontario, Victoria Hospital, and one at the University of Saskatchewan. And it was kind of a race to be the first one to sort of kill cancer with radiation. And the group at Western was the one that won, but only by a scant few days. But it was this is what caught the eye of the media, that there was a race to be the first to come up with the cobalt bomb. This is still one of the main ways that we fight cancer today. We generate this radiation a number of different ways. We use accelerators today in many parts of the Western world, but we still use cobalt in machines that are shipped around the world, and that cobalt is still made at Chalk River in the NRU reactor. So the yin and the yang of nuclear has always been the military and the peaceful side of it. There is no solid demarcation in that the uranium which splits, or the plutonium which splits and releases energy in an atomic weapon, is the same fundamental process that happens in the NRU reactor, or the ZEEP reactor when it was built, the first research reactor, or the CANDU reactors, which is lighting up half the lights in the room today. So that yin and yang has always been there. So right from the beginning, there was a recognition that if we owned this knowledge, we being the United States and other countries that had it at the time, we need to keep this from getting out to the rest of the world. And the policy of keeping it to yourself didn't work very well. And so eventually, the International Atomic Energy Agency was developed as the watchdog to watch the other countries that have nuclear science. There was a decision that there are some good things that you can get from nuclear science, and countries need to have this ability to pursue nuclear science for medical reasons, for energy reasons. But at the same time, we don't want them using that energy to make nuclear weapons. Now, it's fairly simple to monitor that this doesn't happen in most cases. There are ways to get around it, and I'm sure you're aware of some of the classic cases you hear about in the news lately. In fact, just this week, with the visit of the Israeli Prime Minister to the US talking about one particular country. But generally, the process of monitoring peaceful nuclear energy around the world has been very successful in that there are hundreds of countries that are being monitored. And because the process is fairly simple, you sort of have to go in and count the fuel, and then you come in on a regular basis and count the fuel. And if there's something missing, then there's a flag that goes up. And nobody generally wants to be the person that's caught diverting fuel from a peaceful nuclear program. Because you have such a big advantage from having nuclear power in your country, it's generally not something that people want to do. If you want to have a nuclear weapons program, there are far easier ways to pursue that than messing around with a peaceful nuclear power program, with much less investment, actually, because you don't have to use your $4 billion machine to do it with, which is under a microscope of the international community. So Canada had a big part in the start of this, and we've been on the board of directors of the IAEA ever since, and playing a big role in developing technology for monitoring the movement of fuel. All the fuel that's in power reactors in Canada is monitored from the moment it arrives at the station, as it goes through the station, and when it's stored afterwards. We make technology which is used on other reactors around the planet, and we have been a big player in supporting through the Department of Foreign Affairs, the IAEA, ever since its inception in 1957. So we got our start in peaceful applications by building devices that can cure cancer, fight cancer. But the big ticket item for nuclear energy was always seen as as nuclear power. Because with nuclear energy, the unique thing about it is that you have millions of times more energy per unit mass than any other form of energy out there on the planet. Until this was discovered in 1939, everything we had done on the planet as a species was using less than 1%, far less than 1% of the available energy of the universe, if you want to look at it that way. In 1939, we discovered how to crack into that other 99%. And so shortly after they did that, people started thinking about ways that you can use this energy to make electricity. Now, it took a number of years to get around to that point, and we also didn't have a big rush at the time because there was lots of falling water to exploit. There was a lot of coal on the planet. There still is a lot of coal on the planet. There's no problem with coal as far as abundance. Its issues are always to do with the emissions that come at the other end of the cycle. So there was economic reasons, though, why a jurisdiction like Ontario started looking at this new source of energy that it was aware of and keeping a watching brief on. But in the 50s, it started collaborating with Atomic Energy of Canada, as we were known then. And so the federal nuclear agency and the provincial utility started working with an engineering company, which was chosen to be Canadian General Electric, which is now GE Canada Hitachi, I think it's called, in Peterborough, Ontario. And they designed the first CANDU reactor, the first Canadian-designed power reactor using heavy water, the same material that was being explored in Paris and Cambridge and Montreal and Chalk River, and to make one of the world's most efficient, flexible nuclear reactor designs. This is the basis of the CANDU reactors today. Things have evolved since this design, but this was essentially the basis of the design today. So in 1962, we had our first power reactor. We've gone on to build more power reactors in Canada. They're mostly all in Ontario. About 25 have been built in Canada over the years, of which I think about 18 are running today. So there's 8 at Pickering. 6 of these are running today. There's 4 at Darlington, which is in Oshawa. There's the nuclear power demonstration, the first one, this is actually just west of Chalk River, so it's near Ottawa. Douglas Point is the first large-scale prototype CANDU reactor, and that's at the Bruce Nuclear Station on Lake Huron. And also at the Bruce, you have 8 larger CANDU reactors. 4 you can see in the picture here, and 4 off the picture to the top. There are 2 in Quebec, both not operating today, and there's 1 in New Brunswick, which today is providing about 30% of that province's power. So again, about half the electricity in Ontario, and most of the nuclear reactors are in Ontario, and one operating nuclear reactor in New Brunswick. Around the world, we are the other way of making nuclear electricity on the planet. There is the American design, the light water reactor design, of which there are many variants and many other countries making that design. And there's the Canadian way. So we have a very small slice of the nuclear pie out there in terms of numbers of reactors. There are over 400 power reactors on the planet, and about 30 of those are heavy water Canadian-style reactors. But we are the other type of nuclear reactor out there, so it's quite an achievement. And people who have CANDU reactors don't have to buy enriched fuel from the few places on the world that have enriched fuel production industries. And so the fuel comes in, it's just natural uranium. That's the big attraction of it. That's why Canada developed this method in the first place, is we don't have an enrichment capability. Enrichment meaning you take the uranium out of the ground and you make it more concentrated. We just take it out of the ground, turn it into fuel, and put it into our reactor. So it makes the fuel cheaper, and you also get about twice as much energy out of it that you would per pound, per gram, than you would if you have an enrichment process. How reactors work? Well, here's the pie chart of Ontario. The blue is nuclear, and this is the production of electricity yesterday at it's 2:45 in the afternoon. For all of Ontario. So I got this off the Canadian Nuclear Society website, which the address is at the bottom there. You can get this and it'll tell you at that instant where is the electricity coming from in your province. So the orange is hydro, that's mostly Niagara Falls and the Saunders Dam at Cornwall. And then you have the gas, which is yellow, and the green is wind, which was 6% and a bit at 2:45 in the afternoon yesterday. On that same website, you can see the proportion that comes from these different sources over the last 48 hours. So now, which is 2:45 in the afternoon yesterday, is on the right hand of the screen, and then you go progressively backwards in time, 48 hours. The light blue is the nuclear production, and you can see it's steady state, virtually. It's a little blip there where it increases in the last little bit, but it's mostly steady state. That's the baseload power supply for the province itself, the nuclear portion. Hydro is the next biggest portion, which is the purple. And over 48 hours, you see that it goes up and down because in addition to the large dams at Niagara Falls and Cornwall, you also have many other dams that get turned on during the day as electricity is needed in bigger supplies. Below that, you have the natural gas also fluctuating as demand drops and increases. And then the wind is the portion below that, which is, I guess, it's a green line with gray under it. So you can see it rises and falls. And the wind isn't following any fluctuation in terms of demand. The wind is following a fluctuation of supply. It's used whenever it's blowing, and you use it to its fullest capacity. So this is the CANDU reactor. All the fission happens on the inside here. This is the containment building around the whole shooting match, and that is the round concrete structure you would have seen in the Pickering picture. Everything else about this over on the right is just a steam engine. It's just a classic steam cycle where steam is created in a big kettle where water is boiled by the heat of nuclear fission. That heat could come from the burning of coal, the burning of anything. And then you have the steam used as a fluid which turns the turbine and makes electricity. Okay, so this is that same building. It's a very complicated structure if you look on the inside. This is just a CAD drawing of it. The reactor itself is the green thing in the center there. There we go. So that's the reactor itself. You see it's the smallest thing in the building. The rest of the building is full of the paraphernalia for taking the heat out of the reactor and the safety systems for making sure that all of that stays in that building. This is what I call the what-if building. This is probably the strongest civilian structure we have, maybe the strongest any structure we have on the surface of the planet. This and reactor buildings like it around the world. 5 feet thick concrete, and I call it the what-if building because good engineering is designing a machine that does what it's supposed to do with all sorts of safety systems that you have thought of to cover off what can happen. And excellent engineering is saying, what if we made a mistake? What if we missed something? So let's put a big building around the outside that we call the containment building. We know how much energy is in this system because we know how much heat is there, and we know how much water is in this system. And if that heat meets that water in the wrong way, that water can turn to steam really quickly, which creates a pressure spike. So civilian engineer, go away and build me a building that can withstand that pressure spike, and that's the type of building. As an example of what if, we didn't plan these buildings to withstand the strike of a 747 being driven by a crazy person. So after that happened in 2001, the question was asked, what if that happened to one of these buildings? And it's not a straightforward answer because these buildings have been designed against pressure increases from the inside out, not the outside in. It just so happens that they're robust enough that it would withstand that as well. And that kind of an eventuality is part of the design of these buildings going forward. So nuclear fission, a couple of slides on that. A slow neutron, by slow I mean about 1 kilometer per second, which is slow for small particles, hits a uranium-235 and splits it in half. Big deal, you say, but that was not known until 1939. Until that point, they thought they could just knock off one of these red balls or yellow balls, or maybe 2, or maybe 3, but not split it in half. It splits in half because uranium is the heaviest element that nature allows on the planet, possibly in the universe. It's the heaviest element. Other elements can exist, but they don't exist very long, so uranium is the one that sticks around the longest. And it's the heaviest because nature doesn't want anything bigger than that. So you add one more neutron, one more subatomic particle, that's the last straw, and it splits apart. Seems very simple, but they thought it was very simple at the time when they discovered it, but it took them a long time to come up with that. When they discovered this, they also realized that a lot of heat comes off, millions of times more heat than any chemical process. That's interesting in itself, but also the fact that 2 or 3 more of these particles come off, which means this is the same particle that started the whole process. Now you have a chain reaction, the possibility of being self-sustaining. That's what George Lawrence tried to do at the NRC labs in Ottawa. in the early 40s, and he failed at that, but he was able to split the uranium atom and release some of these neutrons and prove that it was possible, and he knew how much more uranium or graphite he needed to put in one place. He just knew that he also didn't have access to that kind of material. So this was the process that amazed science and really turned everything on its head in 1939. Because not only do you have lots of energy, but you've got a way that it can be self-sustaining. Just as an aside, those neutrons come off too fast, so you've got to slow them down. And that's what the water is for. You bounce the neutrons off the molecules of water, as simple as that. They slow down, they hit more uranium, and there's your chain reaction. That's what a reactor is. A nuclear weapon is the uranium without the water there. A nuclear reactor is uranium with the water in a way that the energy is released at a much slower and controlled process, and there is no possible way that it can explode like a nuclear weapon. So the yin and the yang doesn't exist in terms of the reactor itself, but the nuclear science is where you get the crossover of knowledge. It doesn't need to be heavy water, by the way. It can be light water or regular water as well, which is the other type of reactor design. So what happens in a CANDU reactor is you put a bunch of uranium, which are the yellow rectangles, with, there you go, uranium with the blue is water around it. The neutrons are the black arrows. They bounce around. And energy is released. The water flows over the fuel, takes the heat away, boils more water, which turns into steam, and then you have your power production. There's a picture of a reactor there being built. So you can see it's a big cylinder on its side. A cylinder on its side with tubes going through it. A fancy word for that is calandria, so they chose that back in the day. It comes from the, sort of a heat exchanger industry term. And this is actually a relatively small calandria. The next one, I think, is a bigger one. So this is more the size you would have at the Darlington plant in Oshawa. You can see lots of tubes, and inside each of those tubes is 12 CANDU fuel bundles. 5,000 of these CANDU fuel bundles in total. Each one is about half a meter in length. And when it's operating, you don't have people standing in front of it like that because it's very hot and lots of radioactivity in this particular part. This is now the center of the What If building. And you can see a lot of water coming in on the side through these tubes. And imagine the plumbing nightmare that had to be solved to get this to work on an efficient basis. But it does. And it's an amazing piece of Canadian engineering. This slide just shows you that the process is basically the same thing as fossil fuel. So you have, on the right, if you look at this section here and this section here, it's basically the same. It's a turbine and a generator. And the main difference is how the heat is created to boil the water. Another big difference is where the waste products go. And so the waste products for the nuclear station end up in the next room where they're still today, or they're just outside in big concrete bunkers. And the fuel supply, which is thousands of times larger in volume than you would for the nuclear station. But the essential process, the steam cycle, is essentially the same. So I mentioned the room next door where the fuel is stored. This is what it looks like. It's a large room. It's a pool of water. Why is it water? Because the fuel that comes out of the reactor is still warm and needs to be cooled, and it's emitting radiation. It's very radioactive at that point. Why is it radioactive? It's no longer in the reactor. There's no more fission happening, but the material that's left over from the fission process is energetic and giving off radiation. So we need to deal with the spent fuel or the used fuel from the nuclear energy process for a very long time. And everything's got pros and cons. That's the con of nuclear energy, is that you got to deal with very radioactive spent fuel. On the upside is a very small volume of it, and it's solid, and everything is there. So all the waste products are in the spent fuel. What you're looking at in that pool on the right is about 20 years of spent fuel, and it's all there. All the emissions from the process are in the spent fuel. There is no smokestack. So once it's been in the spent fuel for a while, you move it to these above-ground concrete storage containers. They're different designs. So the one on the bottom right, you can see several of them in the upper left. That's an example of some we have at the Quebec station. Each of those holds 4 years worth of CANDU fuel. And it's just what it looks like. It's a big concrete structure, like a big brick, and the fuel is air-cooled. The fuel is still radioactive at that point, but it's all in one place, and there's no energy getting outside of the concrete building. A good question is what happens to the fuel going into the future? So all of the fuel to date is stored as I showed in the previous two slides, at the stations, either in the pool next door or in these above-ground bunkers. A long-term plan in Canada is to basically put the fuel back where you got it from, because nature has been looking after uranium for 4.5 billion years on this planet, or let's say 1 billion years since it last solidified, the rock. It knows how to look after radioactive material. It knows how to look after radioactive material so well that it's very difficult to find the material if you are a company like Cameco or Areva that's looking for this to build a mine. You can't go over the ground with a Geiger counter, a detector, and find it by its radiation. You have to, because it does give off a little bit of radiation, you need to dig down and find it. And the biggest mother lode of uranium in the world is in northern Saskatchewan. It's sitting in sandstone underground with the equivalent of Niagara Falls flow of water going through sandstone. Sandstone is a very porous rock, and it's been sitting there for 1.5 billion years, and it hasn't moved. So nature knows there's various reasons why it hasn't moved to do with the clay overburden and such in the geology, but nature knows how to look after radioactive material. So we have a very good idea of what we can do in a sort of man-made way to imitate that and put the fuel back into the ground, not in the same place, not in Saskatchewan, but in some other place. And that's the idea. Now, there's no rush to do this, so we don't do this yet. This won't happen for many decades from now. The fuel is very small, and it's all in one place. This is sort of looking to the future. The idea is if an ice age comes and wipes out all signs of what we've done on this planet, this still has to be safe. There are very few things that we have that specification for in what we do today, and this is one of them. I mean, we build very good landfill sites, but we don't ask the question what happens in 1,000 years or 2,000 years or after an ice age. And we do that for good reasons with the fuel, because the fuel stays radioactive for that long. Safety and sustainability. So a couple of slides here on the safety philosophy. I've touched on this already. You build a robust system. That's the first thing. Your good engineering is you build a robust system. You make it tolerant of mechanical failure, human error. You run it with multiple computers that can make decisions very quickly. And highly trained personnel. But number two is you assume that accidents will still happen. You build systems to prevent and control these systems and multiple backups. You test these all the time on a daily basis, and you make improvements based on what you've found. The defense in depth principle comes from the world of military strategizing, but you build out from the center. The first thing is the fuel itself being a high temperature ceramic. So it's not a green flowing ooze, it's not liquid, it's not gaseous, it's a high temperature ceramic. It's solid. The fuel is built to sit in a reactor at 300 degrees Celsius for 14 months and 100 atmospheres pressure. Looking after it afterwards is relatively simple, but when it's in the reactor itself, it's also a very robust container of the energy that's being released in the uranium fission. So that's the first line of defense. Around that, you have two independent reactor control systems, so two ways to control the reactor, both under computer control. You have three independent ways to shut the reactor down. You have many independent ways to cool the reactor. In any kind of engineering design involving energy, having a lot of water is a good idea, and the CANDU reactor especially has a lot of water in it. You saw in the picture how big it was. Most of the can that you see, the calandria, is water, and the fuel is the smaller component. If the Fukushima reactors had as much water as the CANDU reactors had, and in the same configuration, they wouldn't have melted down. The tsunami still would have hit, still would have taken away the backup generators, which unfortunately were in a bad place. They're in a better place in CANDU design. But if you had that situation where all electricity was taken away and the water pumps are not moving the water around anymore, if you have enough water to absorb the energy, water can take an intense amount of energy, and it takes a long time to heat it up. And if it's a big enough pot of water in the right configuration, it can actually move around and it can passively take heat away from the fuel. If that happened in a CANDU reactor at Fukushima, the reactor would have just cooled itself and you wouldn't have had the meltdowns. So that's many independent ways to cool the reactor. Number 4. Number 5 is the what-if building around the whole thing. And number 6 is there's an exclusion zone around any reactor site where people don't live on a permanent basis. So that's if you have any kind of an accident, you've got this, your last line of defense. Okay, so that's just a picture of the backup shutdown safety system. So multiple ways to shut the reactor down in under 2 seconds, not requiring human intervention. We do have very smart people working at the nuclear stations in the control rooms. We don't have Homer Simpsons there. They have the equivalent of training in terms of time of a medical doctor, and they make about the same salary when they start. So it's a highly trained profession. They know the systems up and down. Again, they're not credited for reactions, for having a reaction in the first stages of any accident. That's given to the computers that have much better reaction times, but the humans themselves also play an integral role. Sustainability. So on that aspect, I talked about all the toxics being contained in easily managed small amounts of fuel, which is low in volume. All the spent fuel generated since 1962, which is when our first reactor was built, would cover a soccer field to the height of a player. So if you took it all out of those pools or those above ground concrete structures and stacked it up on one soccer field, it would go about 5.5 feet high. Interestingly enough, that's about half the volume of garbage generated in Toronto on a daily basis. So all the spent fuel generated since 1962, half the volume of municipal garbage generated in Toronto. I'm not comparing the toxicity there, although I wouldn't eat the garbage generated by the city either, but it's not an issue of volume. It's not an issue of where to put the fuel, it's the radioactivity and the control of it. Long-term management is something that is an ethical question being answered by the Nuclear Waste Management Organization, which is a federally designated agency which by law has to be putting this technology in place. And as I mentioned, there's no rush to do this. So they're currently choosing a host community, which has to be a volunteer host community. They have 9 communities in Northern Ontario and at the near the Bruce plant in Lake Huron. And they're working through this process. There's lots of time to get this into place. Okay, so a CANDU bundle, which I usually bring with me, but I didn't today. Forgot that bundle. It looks like this thing on the left. It's a 1/2 meter in length. This is the unit of power that goes into the CANDU reactors. There's 12 of these in each channel, and there's 4,000 to 5,000 of these bundles in each reactor. And one of them is enough to provide electricity for a home, for a family, for 100 years. So if you ever wondered, if I got all of my electricity for my entire family, for our entire combined life, from one power source, how much fuel would that take? And that's the answer. It's about this big, this long, and this diameter.
How much uranium is there?
How much uranium?
Yeah.
There's 19 kilograms of uranium in that object. When it comes out of the nuclear reactor, it looks just like that. And there's 19 grams of uranium in it, plus some of the waste products of the uranium, which is what's giving off the radiation. And so the other way to ask that question is, if I got all my electricity from one power source, what would my footprint be? And that's your footprint. It's an object this long and this diameter, which has to be managed, just like the waste products from any power generation system have to be managed, but that's it. And that's really the reason why we pursue nuclear energy in the first place in Ontario. It has to be economical and it has to be clean. It's the second cheapest way to make electricity in Ontario, so it's economical. You can't beat falling water for being economic. Coal is very cheap too, but we don't burn coal anymore. But it's about as cheap as coal. And it's clean. All the toxics are in one small item. And that's not a surprise. Remember, 1 million times more energy than any chemical reaction, so that's the advantage you get. If you wondered how much that would be in terms of fossil fuels, that bundle the size of a fire log is equal to 400 tons of coal, or 60,000 gallons of oil, or 10 million cubic feet of natural gas, and they have their environmental repercussions as well. So natural gas is used, as you saw on that pie chart, it's used quite a bit in Ontario because it's cleaner than coal. It still produces 2/3 of the greenhouse gases that coal does, so it's cleaner, but it's not the cleanest source of electricity. But you still need to burn natural gas. You don't want to have just a system running on nuclear power. You don't want to have just a system based on solar power. You want to have a mixture. Because as you can see from that slide that I showed with the variation over time, some things run all the time and some things are turned on and off, and you need a variety. Nuclear happens to be really good at running flat out all the time, so it's a 24/7 power source. So contribution to world peace. I think I have about maybe 2 more slides here, 3 more slides. So this is my brainstorming on all the ways that it contributes to world peace. So nuclear weapons don't contribute to world peace, although that can be argued as well, but I'm talking about nuclear energy. So nuclear energy does reduce our dependence on oil, right, which comes from certain areas of the world that are centralized, and you would sure diffuse a lot of tensions in the world if you didn't depend on oil. Now, we're not going to get away from oil, but anything that helps us get a little more independent is in the right direction. Nuclear energy, through the development of cobalt cancer therapy and nuclear medicine, gives access to health improvement in countries around the world. You don't have to have a PET scan machine in a country in the middle of Africa to examine the insides of a human body and determine how the heart is working. But you can get some nuclear medicine in a vial that comes in on an airplane from Ottawa, Canada, and a technician there can determine how the person's heart is working. With a very simple technology compared to something which runs on an accelerator-based technology like a PET scanner. Food irradiation, we don't do a lot of that in Canada, but it is licensed. Now this is using the energy of radiation to kill pathogens in food. There's absolutely no reason to have E. coli concerns in beef because you can kill that with radiation. That's done in some places on the planet. But we don't do that in Canada because there are political concerns. People don't like seeing signs in the supermarket that says this food has been irradiated. You can treat food in different ways to kill the germs that are in there. You can treat it with heat, chemicals, or radiation. Okay, so all of them are intrusive in their own special way. Some things that we irradiate to make them to kill the bugs, it's the only way to do it. For instance, how do you kill pathogens? How do you kill bacteria that's on a Band-Aid? Once you've taken the Band-Aid and you've put it into the wrapper, how do you sterilize it? You can't add chemicals because the Band-Aid is wrapped up in its sterile container. You can't heat it because it's a paper product, but you can pass radiation through it, which is just energy, and the energy kills the bacteria. So every Band-Aid that you put on has been irradiated from cobalt-60, more than likely made in, not Chalk River, but in the CANDU reactors in Ontario, because they also make cobalt-60 on the side. We reduce our environmental impact of electricity production, as I've already discussed, and the aspect that I actually work in professionally is controlling the spread of nuclear weapons via the nuclear non-proliferation treaty. So the most effective way to, as I mentioned, to monitor that people are not progressing on a nuclear weapons program is to go in and count every atom of uranium and plutonium they have in their industry. You know, uranium is the most abundant mineral in the Earth's crust, so you can't count every uranium atom, but you can count the ones that are in their industries, whether it's power industry, medical industry, in their labs. How do you go into these countries and count those? You can't just go in. We can't just violate a country's sovereignty and go in and count the uranium atoms. You can go in there if they have a nuclear power program, and the only way they can have the nuclear power program is by signing into the Non-proliferation Treaty. So I would say it's the most successful treaty on the planet. There are a few exceptions where it's not worked. There are ways to get around everything, and so there are a few countries that have developed nuclear weapons despite the Non-proliferation Treaty. Some of them have never signed the Non-proliferation Treaty, so they're not really violating anything. Others were in the Non-proliferation Treaty, like North Korea, and then abrogated and developed a nuclear weapon. So there's specific cases where it hasn't been successful, but there's 180 odd cases where it has been successful. And it's the only way to having the nuclear power program is the only way that we are allowed to go in on a weekly basis and look at their power, walk into these buildings that have the fuel in the pools and actually look at them. And these are highly protected, secure buildings, lots of sovereignty concerns and commercial concerns and proprietary concerns, but these inspectors from the International Atomic Energy Agency can go in and count the fuel. All right, a couple of slides with pictures. This is nuclear medicine in practice. So the upper right is actually two different things. The upper right is cobalt cancer therapy. So that's taking the radiation from the radioactive decay of cobalt-60. The cobalt-60 was created in the NRU reactor at Chalk River, and you're passing the beam of energy through cancerous tissue and killing the cancerous tissue. The other picture is nuclear medicine, which is a bit different. That's taking radioactive material and injecting it into the human body in small amounts and turning the human body into the creator of the energy. So instead of having an X-ray machine sort of puts energy through the body itself is creating the energy. And you can see that it lights up like you would think. You can follow then how somebody's metabolism is working. If you get them to run on a treadmill, and you are looking at where the blood flows and looking at the heart, and part of the heart's not shining like this, and that part of the heart's not getting adequate blood flow. And you can do that with nuclear medicine. And it's non-intrusive, and the material decays away and becomes something that's not dangerous within the day. So it's something which is done quite extensively around the world. There's about 80,000 treatments in North America alone every single day using nuclear medicine. A large portion of that comes from Chalk River, Ontario.
It says 50,000 on the screen there, 50,000.
80,000 in the whole world. It's a hand-wavy number to begin with. Okay, so the Non-proliferation Treaty. This is more than just pictures, there's a little bit of words, but 1953, we talked about this already. So 1953 was the Atoms for Peace Declaration, and that was the United States saying, we're not going to hold on to this technology. There's good things that comes from this technology. We're going to let the world use it, and we're going to make sure they don't use it for nefarious purposes. Canada got in on that right from the beginning and helped start up the International Atomic Energy Agency. We stopped exporting in 1965 of uranium to countries that were building nuclear weapons. By the way, this doesn't mean, because we decided to pursue peaceful purposes, that we never had nuclear weapons in Canada. We had nuclear weapons in Canada through NATO. We just didn't produce them ourselves. They were American nuclear weapons. So 1970 was the Non-proliferation Treaty, which isn't just about non-proliferation, which is stopping the spread of nuclear weapons, but it's also about disarmament and encouraging nuclear energy. So there's these three pillars: disarmament, non-proliferation, nuclear energy. Of those three, disarmament has had the least attention since the NPT started. There's not a lot of countries that have disarmed from nuclear weapons. But it is one of the three pillars of the NPT. So 1972, we signed a comprehensive safeguards agreement, which basically says we're opening up our facilities to the IAEA to come and inspect. And in more recent years, they've strengthened those agreements since what was discovered in Iraq, previous to or after the first Iraq War, which was that you can actually be in the NPT, the Non-proliferation Treaty, and you can be complying in every way and still have a weapons program on the side. And the reason is because those inspectors do come into your country, they do look at the fuel in the pool, but then they're only allowed to look at the facilities that you have declared. So obviously there's a loophole there. That loophole was closed after that, and now this thing called the additional protocol, in the last bullet here, was created, which says, when we come into your country, we would like to look around at anything we want to. And by the way, we have to do that within a certain time frame as well. Not next year. We want to see that in half an hour kind of thing. And so you can go look at the laboratories and the universities. You can look at any bunker you think is interesting from satellite imagery. So some bitter lessons were learned after the first Iraq War. That's that. So some more information if you want it. That's my company's website at the top. The federal regulator is the Canadian Nuclear Safety Commission. They have lots of information on both how we meet our international obligations in counting the uranium atoms in Canada and helping the world, but also on nuclear safety. The third one is my own personal website, Nuclear FAQ. Please write to that if you have any questions that aren't answered today. If I can't answer the question, I know people who can answer them for me. And my personal email is at the bottom, and that's how you can get a hold of me. So thank you.